Assalamualaikum and good day. We are from Section 01, Group 5, Engineering Fluids Mechanical Labs are about to present our Lab 3, which is related to fluid friction flows in pipes. My name is Muhammad Aslam Tukanai, my meeting number is M019303 and I am from Kuantan. First, let's see into the background of the frictions. The man behind the principle of friction is Leonardo da Vinci. Leonardo da Vinci had spent almost 2 decades investigating friction and its application to a variety of mechanical failures. He recognized the critical role of friction played in the operation of machinery and how friction had affects efficiency. Leonardo was the first person to document the principle of friction, which he accomplished by performing experiments with pulleys, strings, and weights. The friction he discovered was a significant factor in restricting the effectiveness of machines, even though it was sometimes beneficial and even necessary, where his discoveries of friction have been the foundation for understanding friction in a fluid system. Next, let's see the background of the friction loss in laminar and turbulent pipe flows. Friction for a fluid arises when two fluid layers move in opposite direction and form an internal flow resistance known as viscosity. And this viscous fluid is known as Newtonian fluid. When this fluid flows, the viscosity will come into effect, which causing laminar or turbulent flows. The flow of the fluids in pipe can be determined to be laminar or turbulent by looking to the value of its Reynolds numbers. The problem statement of this lab is when the fluid flows across a pipe network, it will produce two types of energy loss that contribute to the reduction of the total energy for the flowing fluids, which are major loss and minor loss. The major losses are caused due to the friction from the viscous effect of the fluid that occurs along a straight pipe. Meanwhile, the minor losses are formed due to the effects of the various piping system components such as bands, elbow fitting, valve, and pipe size. In this experiment, the pipe friction losses are being investigated to address the problem of fluid friction in pipe system under varied conditions. The objective of this lab is, first, to study and apply the fundamental knowledge of minor and major losses in varied pipe conditions. Second, to understand and elucidate the principle behind the occurrence of fluid friction in pipes. Third is to measure and investigate the fluid flow velocity and head loss for straight, elbow, and bent pipe conditions for different type of diameter under different type of flows. The fourth is to understand the mechanism of fluid friction phenomena in pipes. For the lab scopes, we will examine and discover the occurrence of friction losses in different pipe shifting conditions by looking into the major and minor losses that form due to the influence of pipe head loss and pressure loss. Here, the experiment will be conducted and assessed in a straight pipe condition for the major losses, and will be carried out in elbow and bent pipe condition for the minor losses case. The pressure inside the pipe will be measured by the use of a pressure sensor. And furthermore, we will investigate how the change of size in length and diameter of the varied condition of pipes will affect both head loss and volumetric flow.
Assalamu alaikum, my name is Abdul Fattah Al-Hamdi. Today I'm going to talk to you about chapter 2, which is theory. Now going for the fluid friction, the precise determination of static pressure drop and energy loss or head loss in a pipe systems in a fluid dynamics issue that mechanical engineers frequently face. This may involve the movement of fluids through various hydraulics and pneumatic systems such as water, oil, and natural gas pipelines, and so on. And this experiment we will analyze the head loss caused by friction pipes in the pipe fitting at a different flow rates via pipe network. In a fluid flow, a friction loss or skin friction is the loss of pressure or head caused by the fluid's viscosity at the surface of a pipe or duct, and that what it will benefit us and what will we gain. And then in mechanical systems such as internal combustion engines, this phrase refers to the power loss in overcoming the friction between two moving surfaces, a distinctive phenomenon. And the both static pressure drop and energy loss by the pipe network are necessary to establish the required pump size. So going to the laminar flow and the turbulent flow. The laminar flow losses are proportional to fluid velocity. The V is the velocity of the fluid. fluctuates smoothly between the bulk of the fluid and the pipe and the surface, which is zero, and the roughness of the pipe surface does not affect the fluid flow or the friction loss. In turbulent flow, losses are proportional to the square of the fluid velocity. At the viscous sublayer, a layer of chaotic eddies and vortex forms the transition to the bulk flow. It's important to quantify the roughness as the ratio of the roughness height to the pipe diameter referred to as the relative roughness. And what is the flow of Reynolds, or when the flow of Reynolds will be unstable between 2000 and 4000 Reynolds number, fluctuating over time as random vortex form and disappear. So going to the second part, the theory formulas. To calculate the overall friction loss, the sources from friction are occasionally reduced to an equivalent pipe length. The energy loss in a pipe may be calculated by applying the energy equation to a piece of straight pipe with a constant cross section, as in the equation. As well, and if the pipe is horizontal, but the head loss equation due to friction can be calculated from the Darcy equation. Due to frictional resistance, the pressure differential, pressure out minus pressure in between two places in the pipe, is caused, and the head loss HL is directly proportional to the pressure difference, which in the equation HL is the head loss due to the flow resistance, F is the Darcy coefficient, L is the pipe length, the D is the pipe diameter, and the V is the average velocity. The G is the gravitational acceleration. The Darcy coefficient or friction factor of laminar flow is entirely a result of Reynolds number, Re. It's independent of the surface roughness of the pipe, and Reynolds numbers is given by or can be calculated by this equation. This experiment directly monitors HL using water manometers and a different pressure gauge linked to the test pipe pressure tappings, where the equation V is the average velocity, D is the diameter of the pipe, and mu and nu are the fluids, dynamic and kinematic viscosities respectively. So the minor losses, the majority of the pipe system consists of much more than straight pipes. The extra components contribute to the system overall head loss. And you can see the slight losses can be mitigated by the pipe entry and exit, rapid expansion, and so on, and elbows, bends, and tees. So the major losses may not be as little as they appear. For example, a partially closed valve can generate a bigger pressure drop than the lighting pipe. So that's all from me. Thank you very much.
Assalamualaikum warahmatullahi wabarakatuh. My name is Fatin Syairah binti Yusuf and my matrix number is MA19196 and I am from Machang, Kelantan. I will explain about chapter 3, which is method and procedure. Firstly is equipment and materials. We use fluid friction apparatus, hydraulic bench, pressure sensor and flow rate indicator in this experiment. Next is experiment setup. First is install the fluid friction apparatus experimental unit so that the drain is above the volumetric tank. Unscrew the rear star handle bolt for pressure gauge attachment and slide the gauge down one hole before tightening the star handle nut again. Connect the hydraulic bench to the unit using hose. Open the fluid friction apparatus drain while closing the main valve. Turn on the pump, gradually open the main valve. Connect the pressure gauge to the apparate measurement location. Next is slowly open the ball cork in front of the selected measurement portion and vent the dual pressure gauge. Regulate the water level on the pressure gauge. Stop the time necessary to fill the volumetric tank to 10 to 30 liters. The drain valve beneath the tank must be shut down. Release the drain valve to allow water to escape back to the bottom sump. Do not let the pump run dry. Next is procedure. For the pipe flow friction factor, firstly is the fluid flow device is placed in the proper section, which is section A. Assemble the fluid friction apparatus according to the experiment arrangement. Adjust the dual pressure gauge to the proper water column head. With the pump running, several distinct variations of fluid flow are changed to obtain 7 volumetric flow and heat loss reading. Lastly is record the necessary values. Next is for the pipe elbow loss coefficient and equivalent length. Firstly is use the appropriate section of the fluid flow apparatus, which is section B. The fluid friction apparatus is assembled according to the experiment arrangement. The dual pressure gauge is adjusted to the proper water column head. The pump is adjusted so the volumetric flow is at maximum. Next is connect the dual pressure gauge to the pipe elbow, which is first set of elbow. Record the data of the head loss. For the lastly is for the pipe bend at and the 55 degree pipe angle. Repeat step 5 and 6. That's all from me. Thank you.
Salam Sejahtera and good day everyone. With myself, I'm Dina, metric number MA19218. Okay, today we're about to see the chapter 4, which is a result graph and discussion for the lab 3, which is known as the fluid friction flow in pipes. Okay, now we're about to see the experimental results obtained, which starting from the pipe flow friction factor for the straight pipe flow. As you can see, this is the obtained volumetric flow, which was in the unit of liter per minute, and followed by the measured head loss, which is in meter. As you can see, the obtained measured head loss uh, decreases over time as the volumetric flow increases. Okay, now let us see the pipe elbow loss coefficient and its equivalent length. This is the results for table 4.2. As you can see, it's an elbow pipe for 90 degree, and the volumetric flow liter per minute shows an increase as well over time, and the measure head loss also can be see increases as well. And for the bend pipe 90 degree, see the volumetric flow increases, and the measured head loss increases as well. So for the bend pipe 45 degrees shows the same increase in volumetric flow, and also for the measured loss shows an increase as well. Okay, now let us refer to the analysis results. Uh, Starting from the straight pipe flow, the values obtained consist of volumetric flow speed, Reynolds number, Blasius pipe friction factor, and followed by the calculated measured head loss and also its variance. So for the straight pipe flow, we can observe that the difference in its variance is very small for every part of its values obtained, as you can see in the table. So and followed by the pipe elbow loss coefficient equivalent. So the same method has been used to obtain the values in elbow pipe 90 degree and the bend pipe 90 degree, and also the bend pipe 45 degree. Okay, now let us refer to the discussion part. Starting from the pipe flow friction factor. So the first question is about what conclusion can be made from the head loss at the flow speed. So I would say that the higher the flow speed, the greater the rate of the loss will increase. So evaluating the Darcy equation, it offers and causes of influencing pipeline and head losses. So the second question is what would happen to the head loss if the length of the pipe is increased. So you can say the head loss doubles when the pipe length is doubled as well. So the head loss of the fluid velocity is directly related to the pipe length, the square of the fluid velocity, the friction factor, which will accounts for the fluid friction. So the next question is what would happen to head loss if the diameter of the pipe is increased. I would say the inner pipe diameter when increased, the head losses will be cut by half. So when the flow rate is twice, the head loss multiples by 4. Using a conduit with a small diameter, the return power output will significantly increase head pressure. So for minimal head pressure, it is optimal to use the greatest diameter pipe as possible. So for the next part is about the pipe elbow loss coefficient and equivalent length. So the first question is about what is the relationship between flow speed and head loss. So since the flow velocity is directly proportional to the volumetric flow rate, so the system head loss must be exactly proportional to the square root of the volumetric flow rate. So from this connection, we were able to say the system head curve loss versus volumetric flow rate may be derived. So for the second question, what is the connection between the elbow and bends in terms of turning radius, head loss, and coefficient? So the fluid flow or the curve is the presence of radial pressure gradient caused by centrifugal force. So result, the fluid pipe core travels and the outer wall returns to the inner wall, which will result in diverse spiral flow. So resulting a significant increase in pressure losses. Even relatively large radius bands, flow free will be significantly warped, and also the both friction and momentum changes arising from the change in the flow direction, which contributes to the pressure loss in a curve. So the third question is, what is the conclusion can be made considering the elbow and bends in terms of radius and equivalent length? So these variables are dependent on the bend angle, so the curvature ratio and the Reynolds number. So the overall pressure drop can be expressed in terms of two components, which is the result of friction in straight pipe of equal length, which depends primarily on Reynolds number and the pipe roughness, and also which results from the loss of change of direction, which typically expressed in terms of bend loss coefficient, which curvature ratio and the bend angle.
Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. My name is Haris Nafayin bin Shamsul Azri. My ID number is MA19138. So as for now, I am going to present to you the conclusion of this experiment. So throughout this experiment, we managed to study and apply the fundamental knowledge of minor and major losses in varied pipe conditions, understanding and elucidating the principle behind fluid friction in pipes, measuring and investigating the fluid's flow velocity and head loss for straight, elbow, and bend pipe conditions for different type of the diameter under different types of flow, and understanding the mechanics of fluid friction, fluid friction phenomenon in pipes. So based on this experiment, we came out with the same result in for theoretical and experimental head loss, where it increases as the velocity rises, with the exception of the elbow pipe. So as Reynolds number grows, both the theoretical and experimental coefficient of friction tends to decrease. The experimental calculation result is backed by the theoretical calculation to identify which one had the largest head loss. So finally, we were able to identify which pipe size and material are optimal for specific situations. We also determined that the kind of flow will affect the loss within the pipe. The experiment is crucial to us as students will be extremely beneficial in the future. Thank you. So this is the references that we use throughout this experiment. That is all from me. Thank you.